What is meant by the term polarizability? Polarizability is how easy it is to induce a dipole, how easy it is to warp the electron cloud to get the electrons more on one side than the other. Which of the following atoms would you expect to be the most polarizable? Nitrogen, phosphorus, arsenic, or antimony? The larger the atom, the easier it is to polarize. So big puffy atoms are easy to polarize. The smaller ones are hardest to polarize. Hard clouds versus soft clouds. Put the following molecules in order of increasing polarizability. Again, you're looking at the atoms. Big atoms are easy to polarize, so bromine is the biggest atom there. Germanium's bigger than silicon. Silicon's bigger than carbon. So I expect the one that's easiest to polarize would be germanium tetrabromide. The hardest one to polarize would be methane. Predict the order of the boiling points of the substances in part C. All right, so since methane's so hard to polarize, it has the weakest dispersion force, right? The weakest induced dipole attraction. Therefore, it's the easiest to boil, right? It have the lowest boiling point. The hardest one with the biggest attraction, right? The one that's easiest to polarize would be the germanium tetrabromide. So it'd have the highest boiling point. Most energy to separate. True or false? Oh, we already have there. A is true. For molecules with similar molecular weights, the dispersion forces become stronger as the molecules become more polarizable, right? The more polarizable, the stronger the attractions. For noble gases, the dispersion forces decrease while the boiling points increase as you go down the periodic table. No, the dispersion forces increase, right? The atoms get bigger, so this is false. Atoms get bigger as you go down the group, right? So electrons further out are easier to polarize than tighter clouds, closer in. In terms of total attractive forces for a given substance, dipole-dipole interactions, when present, are always larger than dispersion forces. Well, if you're looking at an isolated situation comparing dipole-dipole attractions to dispersion forces, yes, but with large molecules, you get a cumulative effect with dispersion forces. So I'm not sure what they want with this question. I'd say false, right? Larger molecules can have a cumulative effect in terms of induced dipoles. So you can have a higher boiling point with a non-polar large molecule than a polar molecule that's small. D, all the following factors being the same, dispersion forces between linear molecules are greater than dispersion forces between molecules whose shapes are nearly spherical. Yes. When you have a long molecule, you have more opportunity to get the molecules close to each other and get a greater cumulative effect of those induced dipole attractions. Rationalize the difference in boiling points in each pair. All right, so it's HF, it's 20 degrees Celsius, whereas with HCl, it's a negative 85 degrees Celsius. Well, they're both polar molecules, but HF is capable of hydrogen bonding. So hydrogen bonding is a stronger attraction than a regular dipole-dipole interaction. B, trichloromethane as opposed to tribromomethane. Yeah, you get a higher boiling point with tribromomethane. One, it's heavier. Two, bromine's more polarizable. Bromine versus iodine chloride. Iodine chloride's a polar molecule, so you get a dipole-dipole attraction with iodine chloride, so that's why you have the higher boiling point. Explain why the surface tension and viscosity decrease with increasing temperature. Well, as the molecules move faster, you're getting less molecules attracting each other, right? They're moving too fast for them to grab each other, so the surface tension goes down with higher temperatures. Why do substances with high surface tensions tend to have high viscosities? Well, high surface tension means strong intermolecular attractions. High viscosities, strong intermolecular attractions. Explain the following observations. The surface tension of tribromomethane is greater than that of trichloromethane. I already did this. Yes, it's going to be higher surface tension because more bromines are more polarizable. Yeah. As the temperature increases, oil flows faster through the narrow tube. Well, as you increase the temperature, you break up intermolecular attractions, and this is why it'll flow faster. Raindrops collect on a wax automobile hood. Take on nearly a spherical shape. Well, that's because we have hydrogen bonding between the waters, pulling all the waters together, and we have a weak attraction between the wax and the water because the wax is nonpolar. So strong intermolecular attractions, weak attractions between the oil and the water. Oil droplets collect on a waxed oil droplets collect on a wax automobile hood. They take on a flat shape. Well, because the intermolecular attractions are weaker. It's induced dipole, not hydrogen bonding. Right.